As computer science students, your training naturally anchors on the logical domain. You study network architecture, packet inspection, and how to write impenetrable firewalls. This reinforces the popular cultural image of cyber warfare, an isolated hacker detached from the physical world, fighting battles entirely within a pristine digital void. But that pristine void collapses the moment it collides with physical variables. The virtual world does not exist in a vacuum. It operates strictly and entirely on top of the physical world. All the secure, perfectly vetted code you write becomes strategically useless if the hardware running it loses power or is physically destroyed. To understand modern conflict, we have to look at the cyber-physical dependency loop. Conventional kinetic warfare and logical cyber warfare operate as a single, inseparable system. You know the traditional computing stack, building from the hardware layer, through the operating system, up to the application layer. We must expand this downwards. Beneath the hardware lies a foundational layer 0, the physical environment, providing power, communications, and structural stability. This loop runs in both directions. Disruptions travel from the bottom up when a power grid fails, or from the top down when malicious code executes a command. Because these spheres are deeply connected, altering the state of one realm severely degrades or enhances the capabilities of the other. Every piece of software relies on physical network devices and essential utilities to execute its logic. The logical world is driven by a massive physical footprint, ranging from localized home automation and vehicles up to the dense, sprawling server racks that make up the cloud. These complex computing systems require constant inputs. The moment they are severed from foundational utilities, primarily power and communications, the hardware is rendered completely worthless. Despite this reliance, the civilian infrastructure that supports critical computing equipment is rarely hardened against deliberate cyber conflict or physical attack. Architects counter this extreme vulnerability through redundancy, building overlapping systems and backup utilities to absorb the shock of an outage. Adversary forces recognize this dependency and actively utilize widely available commercial technologies to build their own robust, redundant physical networks. Strategically, targeting an opponent's physical power grid often disables their network much faster than attempting to crack their encryption. This vulnerability scales down from massive civilian infrastructure to the individual systems deployed in military environments, where advanced computing provides critical intelligence. Operating sensitive computer equipment in austere environments, like deserts, presents immense difficulty, as these locations completely lack reliable power or climate control. This operational reality dictates a specific engineering requirement: environmental hardening. Hardware must be placed in ruggedized physical chassis to prevent the catastrophic logical failures caused by extreme temperatures, infiltrating dust, or physical impact. This introduces an operational trade-off. Environmentally hardened technology costs significantly more to manufacture, severely straining deployment budgets. In active warfare, physical durability strictly dictates logical availability. If the hardware cracks, the network goes blind. Foundational infrastructure also includes biological and human logistics. A textbook vulnerability scenario involves a disruption as mundane as contaminated food served in a military mess hall. This purely physical attack incapacitates the personnel required to operate the terminals, leaving the cyber forces entirely powerless without a single line of malicious code. Because of this human vulnerability, defending the logical perimeter requires the deployment of physical weapons. Tools like physical explosives, deployable signal jammers, and heavy mechanical locks are utilized to actively deny adversaries access to critical network nodes. Swift detection and kinetic counteraction are absolute necessities the moment an attacker breaches a physical perimeter defense. A compromised physical perimeter completely bypasses every digital firewall on the network. Physical security is the ultimate prerequisite for cybersecurity. This dependency flows in the opposite direction as well. Software actively controls and alters physical hardware. Modern physical systems rely entirely on underlying operating systems and applications to function correctly. Simple network configuration changes can physically disconnect remote devices. Once the logical connection is severed, restoring it requires a physical intervention or a hardwired backup method. These logical disruptions halt an organization's physical operations, and the ensuing repairs consume significant time and resources. The medical device attack vector perfectly illustrates this. In 2009, the first internet-connected pacemaker was implanted, permanently merging biological function with network security. Because medical implants rely on these network configurations, targeted logical attacks on high-profile individuals bypass traditional physical security entirely to yield severe political impacts. This logical-to-physical danger scales rapidly from individual medical devices to massive, globally important infrastructure. Industrial control systems, or ICS, serve as the critical bridge translating digital commands into heavy, kinetic, mechanical actions. These systems control highly sensitive real-world domains, managing the flow of municipal power, maintaining communication grids, and regulating water treatment facilities. Automated manufacturing represents another highly vulnerable sector dependent on ICS architecture. These networks are classified as ultra-high-value targets. Infiltrating them allows an attacker to use a few lines of altered code to trigger catastrophic physical destruction on a national scale. Two primary opposing concerns dictate all modern cyber operations. First is the defensive mandate, maintaining the uncompromised integrity and functionality of your own physical systems and logical infrastructure. Second is the offensive mandate, actively disrupting and hindering the opposition's ability to maintain their own physical and digital infrastructure. True operational dominance requires a strategy that simultaneously attacks and defends across both the logical and physical battle spaces. Writing perfectly secure code is only half of the modern security equation. Returning to our conceptual model, the traditional computing stack is permanently bound to the physical environment beneath it. Logical software acts as a kinetic weapon, while physical infrastructure remains the true Achilles heel of any logical system. The challenge for future architects is to design systems that anticipate and ultimately bridge this critical gap between the virtual and the physical.